So, good afternoon, ladies and gentlemen. Welcome to the session Recent Results 3. This session is meant for members of community to present their projects which are currently in progress. And we have 4 presentations in this session. They all are quite different nature, as you could expect from this kind of session. And I would like to introduce the first speaker, Udo Peer from Technology University of Graz, Austria. And Udo is working in IEAK, Network Security Group. And Udo will work about real-time intrusion forensics, a first prototype implementation. Please.
I don't think that this is my presentation, unfortunately.
Okay. Let's try again.
Okay.
This is the right one.
Okay. Hello once again. Yeah, my name is Udo Peer. I'm coming from the Institute of Applied Information Processing and Communications at the University of Technology in Graz, Austria. And my presentation today is about a first trial to integrate some basic forensic mechanisms into a network-based intrusion detection system. Not only network-based, we try to use some stack-based and state-driven network intrusion detection systems. So first of all, what is forensic computing? Forensic computing is basically just scattering and analyzing some data free from distortion and or biases, just to reconstruct the original data or what did happen in the past on a dedicated systems. And there we have a great number of challenges and problems that we have to overcome. The first one is that we always have to deal with very huge and very complex systems. And another problem is that these systems are changing very rapidly. And if we want to do some basic forensic investigations in huge and complex systems, then a forensic investigator has to look everywhere in the system, since things can hide anywhere and can hide anywhere in these complex systems. And therefore we need very high skilled people with the right knowledge and the right experience. Since anything we do to this system will disturb at least one small part of the whole systems, and maybe that we lose some very important forensic evidences. And another problem is that we can trust in the forensic tools, but we cannot trust on the operating systems or the systems on which these tools are running. So Heisenberg told us that the more we know about the momentum of an electron, the less we know about the exact position and the exact position of these electrons. So this is the real world. This is the real behavior of systems. And in terms of computers or computer forensics, we have to say that examining or collecting just parts of the system will disturb at least a single other component. And we have another problem, that if we can trust the tool which is used, then we cannot trust the system, for instance. We cannot say anything about the kernel which we are using. We cannot say anything about device drivers which are used. And we have some problems with the so-called chain of trust. The chain of trust is what happens when we are running a binary, for instance, on a maybe compromised kernel, on a maybe compromised device driver, on a maybe compromised shell, for instance. And what we try to do is to do some online forensic investigations. We do not want to do these classical offline forensic investigations. We just try to use an online version of forensic computing, since anything or many things can be done online. Active countermeasures, for instance. And we have a very great advantage, or we can make use of a very great advantage, we are working on the original system. We are working on the original data. And offline forensic investigations are just working on replications or just interpretations of this original data. But we also have two very big problems. The first one is that we cannot go back in time. So we have to be very, very carefully with our decisions in collecting forensic evidences. And we have to react in time. So we are working on a living system, and we have very tight timing constraints if you're thinking about real-time applications or real-time protocols, for instance. So I think a good place for doing some basic forensic investigations is the operating system stack, to integrate some very basic intrusion detection mechanisms into this network stack, since this is the only place in our system where we can, or where we have exclusive access to any network packet, traversing the network stack, starting from the data link layer up to the application layer. And we can integrate this concept very easy into any type of node. I think about routers or gateways up to PDAs, handhelds, and even cell phones or stuff like that. Yeah, and another very important point is that we have to save this information. It's impossible to save this information locally, so we have to add some mechanism to transport this information, to add a timestamp, for instance, on this information, and to transport this information to a remote server. This idea is not really new. You probably know the TCP wrapper. The TCP wrapper was written by Mr. Wietse Venema, and he used the concept to do some active countermeasures, to start some active processes, to learn more about the attacker. And he used a mechanism called booby trap. I do not like this term very much, but anyway, he used this booby trap to start some processes to find out information about the attacker. And he used the finger tool to look or to trace the foreign host and find out what users are logged on and what users are registered on this host. And he is using the simple mail service to move this information to a mail account. So in principle, this is the same approach. Yeah? What we tried is to find a set of suitable protocols or suitable attacks which can be detected very easily into the IP network stack. And this is just a very small subset of possible attacks, starting with IP spoofing, operating system fingerprinting, and blinding the sensors, and even detection of shellcode or even polymorphic shellcodes. So I think that you all know what IP spoofing means and what TCP hijacking means. We all know that this problem is not solved so far. So the only thing we can really do in terms of IP spoofing is to do some ingress or egress checks. Just a moment, I'm sorry. To do some ingress or egress checks. But we can do some additional, I would say, countermeasures. So if an attacker is sending me a spoofed IP packet, for instance, then we are sending the XSYN packet back to the victim. And if the victim is alive, he would not answer with a final acknowledge, he would send a reset. And one idea is to search for this reset. And if the victim is not alive, then we can verify if the SYN value corresponds to the received acknowledged value. Yeah? This might be an information, this might be helpful in terms of intrusion detection and in terms of collecting some forensic evidences. And we can do some active packet tracing, for instance. So we can send a trace route to the victim or to the attacker and find out about, or get some information about the distance and compare this information with the time to leave field of additional received packets. operating system fingerprint is the next very big group of, I would say, very nasty attacks. These are just a few examples of operating system fingerprinting attacks. I just wanted to show you a few of them, like the ring tool, which is using the retransmission timeout, the behavior of the network stack, the retransmission timeout behavior of the network stack. And what I want to show you here is that ring is using a sequence of different methods. And my idea was to use state transitions and sequences as signatures for intrusions. Yeah? And you can see here a possible sequence like a SYN packet followed by additional SYN packet followed by acknowledged packet followed by SYN packet and so on. Yeah? So this is a very clear signature to detect a ring fingerprinting attack, for instance. But there are many more, like Xprobe, which is using a sequence of ICMP packets, and IQ, for instance, which is basically using the same sequence of ICMP packets. But IQ is a little bit more intelligent since IP stops if an operating system was detected successfully. So in terms of Linux, for instance, IQ is using just 2 non-malformed packets to detect the operating system. In terms of Windows NT, for instance, IQ is using 4 packets. And last but not least, you probably know the Nmap tool. Nmap is using TCP as well as UDP test packets. Nmap is using the retransmission timeout. Nmap is using ICMP packets. But once again, we have a sequence of well-known test packets. We have a sequence of test packets to find out the initial sequence number behavior of an operating system. We have 4 test packets to open TCP ports. We have 3 test packets to close TCP ports. So we have a dedicated sequence of test packets. And this sequence can be used as a single signature to detect this Nmap fingerprinting attack. And here we have the fingerprint in terms of Windows XP, for instance. So having a greatest common divisor less or equal than 16 for the sequence of initial sequence numbers might be an indicator for a WinXP machine. Or a response to the simple SYN packet sent at the beginning is answered by an acknowledged SYN packet with an acknowledgement number with my initial sequence number incremented by 1 and an advertised window size of that big. Yeah? And this is a typical fingerprint, and this fingerprint is a dedicated sequence of test packets and can be detected very, very easy by using a simple state machine. And what we are using as a signature is just the state transition of this additional state machine. And here we have the screenshot of our implementation of Nmap detection tool, which was integrated in the original WinXP and Win2K network stack. And here we can see that Nmap successfully detected that Nmap is talking to a Win2K or WinXP machine. But what we tried next was to slightly modify the network stack of Win2K. And these are 2 lines of the original Win2K source code. I hope nobody from Microsoft is herein. Okay. The only thing we did was to modify this simple code line so that no reset packet was sent. Here you can see the original command. If it does not have a SYN packet, the received packet, and only a SYN, then we will send a reset. And what we tried was to slightly modify this simple if clause, and what we got was this screenshot. Nmap could not determine the operating system and kindly asked for if you know this operating system, then please send this information to www.insecure.org. Yeah? 5 minutes, okay. Blinding a sensor is another very serious attack, and solutions for these attacks are already integrated into the Win2K and WinXP network stacks. So the only thing you have to do is to add a single key to the registry. So just start regedit or something like that. Add a single key named SynAttack protected and set the value of this key to 2. Yeah? And by doing this, you are enabling a SynAttack detection mechanism into the Win2K and WinXP network stack. And after setting this value to 2, you can modify the timing behavior of the network stack. You can modify the size of the buffer for syn packets of the network stack. And you can do a great number of very useful tools and things. You probably know syn cookies. Syn cookies is in principle the same in the Linux network stack. And unfortunately, these syn cookies are not enabled by default. So you just have to add this simple line to some of your startup scripts. And you can enable the syn cookies. So what this should show you is that there are already existing mechanisms in our network stacks, but all these mechanisms can be improved by just a few lines of code. So IP spoofing can be added to our network stack by just a few lines of code. Or operating system guessing tools can be detected by just adding tens lines of code to your network stack. And even shell codes can be detected. If we add just, I think, 20 or 30 lines of code into the network stack of Microsoft XP or 2K network stack. So unfortunately, I have to skip the next slide. Just a few words about the implementation. We integrated a small set of intrusion detection mechanisms and forensic investigation mechanisms into the Microsoft Windows XP and 2K network stack, and we integrated the same mechanism into the Linux network stack. What we found out is that in terms of Windows, the code we found was self-explanatory and was very easy to modify and was very easy to use. We didn't find additional information about the implementation of the DCP stack, and doing the setup and doing the setup of the development machine was very, very tricky. So the process of compiling the operating system, linking the operating system, debugging the system was very, very tricky and was only described on 2 sheets of paper. So this was the only information we got from Microsoft. In terms of Linux, we found a big mess. So it was, I would say, even worse than compared with Microsoft to understand what Linux is doing at the TCP stack. But a great number of tools exists, and these tools are very good documented and easy to use. Some conclusions. I would say that stack-based threats are still out there, and especially blinding attacks, like the simple stack attack. The stack attack was a very simple tool to generate a great number of syn packets. And I think that it's very easy to expand or to include some additional mechanism into the network stack by using this proposed concept. And we could integrate the same intrusion detection mechanisms into a very, very small device. I don't know if you know this lightweight IP stack. This lightweight IP stack just uses tens of kilobytes of free RAM and just 40 kilobytes of ROM code. And this lightweight IP stack is used in my lectures about securing network stacks. So this is what I'm using, or what I'm telling my students what they have to do. and they're playing a little bit around with this lightweight IP stack. I have to speed it up a little bit. Yeah, I've talked about the to move this information to a remote server, and fortunately XML-based languages are already existing, like this SNML or this more complex intrusion detection message exchange format. Yeah, and what I have to add at last is, unfortunately, the big problem of this concept is that the set of suitable attacks is limited. I would say there are just 10 up to 20 different attacks which can be detected by this stack and state-based approach. And due to this, the effectivity of countermeasures is limited as well. So this is all from my side.
Okay, thank you very much. We have time for one question, please.
I would not say BSD is similar to Linux. I would say BSD is similar to Microsoft. So I would say this way. Pardon me?
Okay, another short question if there is. This was a short one. Okay, thank you, Udo.
Thank you.
And I would like to welcome the next speaker, Vasilis Hadzianakis. Vasilis is a PhD student in the National Technology University of Athens, and he's working in Network Operations Center of the university and as a researcher in Network Management and Optimal Design Laboratory, or NetMode. And Vasilis is going to talk about network flow-based anomaly detection of distributed denial-of-service attacks. And now we get to Vasilis' presentation. Please.
Okay. Hello. I'm here to talk about our work in intrusion detection of denial-of-service attacks with the use of NetFlow. Well, first a few words about intrusion detection. I'm sure you're all familiar with the term of the IDS. Intrusion detection system is a system that detects attacks. There are several categories of intrusion detection systems. An IDS may be a network or host-based, according to if it detects attack, it monitors a host or a whole network. They also can be divided in misuse or anomaly detection, according to the way they detect the attacks. And finally, there is the category of the distributed intrusion detection systems, that are systems that correlate data from multiple sensors spread within a network. Okay, first a few words about misuse detection. Misuse detection resembles to the way an antivirus system works. The system has a database with known signatures, and the signature may be a standard sequence of bytes in the IP header, for example. And when a signature is matched, the intrusion detection detects the attack. The drawback is that they have to be updated constantly with the new signatures. Anomaly detection checks for variation from what's supposed to be a normal behavior. The entity to be checked can be a user inside the system, and that's an asset for this architecture, a computer or a whole network. They use expert systems, and their main drawback is that they have to be trained to become operational. They have to pass through a learning phase. Well, now let's talk about what is a denial-of-service attack. A denial-of-service attack is an attack to suspend the availability of a service. They can be a denial-of-service attack can be made by only a single packet which is correctly made and uses a known vulnerability, or they may use traffic flows generated from various sources so as to exhaust computing or network resources. The main characteristic of a denial of service attack is that they can target a single host or a whole domain, and that what is important to say is that even active network components are vulnerable to this attack. The uses and effects. The targets may be commercial targets, or they can be used even for cyber warfare or terrorism. Another common use is hacker theft wars, that is wars between hackers for show off. Here's a classic example of a distributed denial of service attack. We have the attacker who, in the first phase, tries to take control of vulnerable hosts. The machines become compromised. It's what they call with zombies. And then the attacker commands the attack, and a great number of sources produce a great number of flows that result in the exhaustion of the computer or the network resources in the target domain. Now, a few words about NetFlow. First, what's a flow? A flow is defined by 7 characteristics. It's a sequence of, or a group of packets that share these 7 keys: the source and destination IP address, the source and destination port, the type of layer 3 protocol, the TOS byte, and the input logical interface of the router that come from. So, what NetFlow does, it stores information about active flows, not only the 7 keys that we said before, but other values such as the number of packets that have passed within this flow, the number of bytes, and timers that indicate how much time has been active or idle. The router stores this information in its main cache and exports it in form of UDP datagrams. Flows are exported when they expire, and they expire when one of the 4 things in the arrow happen. That is, when the inactive timer has expired, that is how much time the flow has been idle, or if it has passed the active timer, which is usually 30 minutes, or even if the cache is full, so oldest flows expired, or finally when we have a TCP flow and it's closed by one of its peer, by an RST or a FIN packet. Now, what we have done is created a system that uses NetFlow. It receives the exported packets and tries to detect an ongoing denial of service attack. It is compatible with NetFlow version 9. It both works with IPv4 and IPv6 traffic, and it uses an anomaly detection algorithm based on metrics and threshold. It is also written in Java language. Okay, now let's see the implementation. It's divided into 2 main modules: the collector, which is the thread that collects the exported packets and stores the data in a local data structure. This thread periodically wakes the detector, who is responsible for calculating the data and matches certain metrics and thresholds that we have set to detect an attack. It also does extensive logging and uses email notifications to alert the administrators. Now, let's see the DOS detection metrics. All metrics are based on deviation from what is supposed to be the standard or normal behavior. The first metric uses the current packets of or current flows from a interface pair. For example, the packets that pass from interface I to J. We check the deviation from what is supposed to be the normal number of packets or flows that pass through this interface pair. The average values may derive from the last periods, what the system behaves in the last 20 minutes, or from the same time zones in the past. That is, if today is 3 o'clock, we check every Tuesday 3 o'clock in the past what was the normal behavior. We take the mean values. The other metric is the percentage of the traffic that passes through the interface divided by the overall traffic. These metrics work in, here's an example. You can see that we had normal traffic and the spikes detected the attack. So these metrics work when the pipe is not full. So you can see this deviation. When the link is already congested, we have to search for other metrics. Such metrics are the number of flows that usually, the number of flows that have a very small lifetime. If we have a TCP attack that generates a great number of TCP flows, flows expire very, very quickly in the cache because of the great number. So we see that there's a great number of flows that have a very small lifetime. Or for the same reason, there is a great number of flows that have a very small number of packets. Another metric that is currently tested is the percentage of TCP or UDP traffic. Every network has standard, or more or less, a standard percentage of TCP and UDP traffic. So if you know the average value, you can compare it with the current and see if there's something wrong. Now, detecting an attack and detecting the target is a completely different thing, because the system, in case that the system has already detected an attack, has to guess who is the target of the attack. To do so, it stores the destination IP as key in a hash table for every pair of interfaces, and the number of packets and flows as values. So when it has already detected an attack, it tries to find which is the destination IP with the greatest number of packets and flows. It says that this could be the victim. This is the attack graph that I explained before. Future work. We tend to do more experiments. For what we have seen in research, there are no standard metrics defined yet. So it's a topic of research. Another point of future work that we want to see into is the detection of worms. Finally, we plan to use this tool as a part of a distributed intrusion detection system. We would like to correlate the data with misuse detection systems and hopefully have better results. Okay, at this point I would like to thank I would like to say that our work was based and inspired on Panoptis, and we had the help of GRNet, the Network Operations Center of NTUA, and the NetMode Laboratory to do this work and to continue on working, because it is still work in progress. Okay, any questions?
Questions? Yeah.
Yes.
Some researchers propose to use as a matrix the number of new IP addresses per time. Is there any relation of such a metric with cognitive?
I'm not sure I understand what you said.
If you monitor the number of new IP addresses.
Yes, for every period we
As a matrix for attack detection.
well, we use for every pair of interface we count the count flows and packets. So when the use of the IPs in the next level, when we try to think to find who is the target.
You observe the system, you have a number of IP addresses. That's the normality. And then you monitor the number of new coming IP addresses in each interval.
You mean the source IP addresses? You mean by the source IP?
Yeah.
You check the source IP, yes. Well, this is not always a very good metric because the source IP may be spoofed. Well, what you can check is the AES. Only the autonomous system that from which the packet originates is true for certain. The IP may be spoofed, so it's not a very good metric.
Okay, other questions?
The information that you gather to detect a denial of service attack, have you thought about how that information could be used to do something about the attack, to remediate the...
You mean about countermeasures?
Yeah.
Well, what one can do is that if it has access to the router, it can use rate limiting in the pair of interfaces. But it's too early for us to do something like that because our system is not very, the results are not 100% true every time. We have false positives. So there's still the need for a human to decide if it is an attack or not. But I guess that the system could automatically apply a rate limiting access list in the pair of the interfaces and reduce the effect of the attack.
Okay, any other questions, please?
Yes?
Do you rely on routers to send in the flow data, or do you use special proxy device?
No, we have used the routers.
Because they don't send all the data, they drop it.
Well,
Well, if you have details, you have enough data anyway.
routers do sampling sometimes, so this is not always a problem. If you don't have to send information for all the flows, but for a sample. So this is a solution to this problem.
Okay, any more questions from the floor?
Another solution is
Sorry, go on.
that you don't use you use routers in the edge of the, and not in the main, the great one, if you know what I mean. You try to go to as low as possible in your tree of your distribution tree.
Okay, one more question? No, okay, let's thank Vasilis.
Okay, thank you.
And the next speaker is already here. It's Klaus Mochalski from the University of Leipzig, where Klaus is doing research towards a PhD degree. And Klaus is going to talk about a real-time packet burst metric.
So, good afternoon again, everybody. My presentation.
Sorry, can you start again?
So, my presentation will be about passive measurements and the real-time analysis of passive measurements and about packets. Because we can assume that packets are the atomic events which you can observe if you observe the behavior of a network. That's why we want to focus on packets and especially on bursts of packets, as they are like the worst case which can happen in a network and which should be avoided. So for a start, the objectives and motivations for this project. We wanted to build a quality of service aware measurement device which can be simply tapped into a network link and then provide you a meaningful reading. And the bottom line brings it to the point. We want to provide network operators with something very similar to a speedometer in the dashboard of your car, which works very well for its purpose of showing you the actual speed you're driving with your car, which is a very useful thing if you want to reduce the cost of your journey fine-wise. And we want to do something similar with for traffic on a network link. So what's important for this? First, the measurement has to happen on a very small time scale. If you are dealing with packets, you have to observe every single packet. And this is a challenge in itself. The whole thing needs to be, or the whole metric, what you read from the meter, has to tell you something about different traffic profiles. So if you have certain applications that need different profiles, for instance, real-time applications, video and audio transmissions, then it has to provide you with proper information so you can judge if your network can stand additional voice over IP connections, for instance. So it should provide useful information to network operators, so it should be easily comprehensible and very easy to read. Everybody should be able to understand it. And it should be useful for both troubleshooting, so the real-time aspect comes in here, and for resource planning, which is more of a long-term aspect to the whole thing. And the last point is basically to provide a meaningful alternative to the commonly used averages of packet rates, averages of data rates, which is the common practice now if it comes to observing the utilization of a link. So basically we want to provide a better measurement for link utilization. So I already mentioned the current practice, just as a summary. The current practice is that routers collect quite coarse averages of packet rates and byte rates and export them to network management stations. And if I say coarse, I mean time intervals in the order of minutes. 5 minutes is a standard interval in this context. And one has to think that that the meaning of averages greatly varies with the length of the interval which you calculate the average about. So if you take 1 second averages, then you get a totally different image than you get if you use 5 minute averages, 5 minute intervals. So to visualize this, on this slide, on the bottom of this slide, there are two pictures, and they show the bandwidth, the observed bandwidth on the University of Leipzig's internet access link. And this is a packet header trace taken on the 21st of February 2003. And these are both pictures refer to the same trace. But the left one shows you 5-minute averages, and the right one shows 1-second averages. And if you would take this to more extreme, if you would use 10 or 30-minute averages, you would get a plain flat line on the left-hand side, and on the right-hand side, if you go down to the packet level, you would see only discrete values between 0 and the link interval. So this is the problem with averages, and we were looking for something to solve this problem. So in the summary, as a summary can stand that on a packet level timescale, a link is either busy or idle. This is the only thing that can be observed on the packet level on a link. So now the question is what to measure instead. There are two aspects to it, or two approaches. I don't really like the words proactive and reactive, but you could view it as the proactive could be viewed as the future of the traffic, and reactive the history of the traffic. Or you say something about what happened to the traffic upstream and what happened to it downstream. And part of the proactive approach is that you can measure and present how much bandwidth is available for additional traffic of a certain profile, which is important. So answer questions like how many voice over IP channels can be transmitted over my link given the current utilization. And you cannot answer this if you just look at the utilization. And the reactive approach would be what happens or what happened. So the past, what happened to my packets. And there's only one thing that can happen to packets in transit over a certain network path. They get delayed. And that's all what happens to the packet. And there's only one extreme value of delay. When it gets dropped, then we have infinite delay. And of course, jitter is another value, but this is only another way to see different delays. So why is delay and jitter interesting? It's interesting because delay causes long router queues. And long router queues in turn cause packet bursts and are caused by packet bursts. So and the statement here is if we know all about bursts, then we know all about the traffic, and more important, we know all about the router's problems. Because a router will run into difficulties in case of bursts. So each packet needs its gap. If you consider the proactive approach, so what traffic can still be transmitted in a certain link, then you need to look at the packet at the gaps. So if you want to transmit additional traffic, you put it into packets and put each packet into a gap. And it's important to have a gap of the proper size, and it's important to have a proper distribution of the gaps, so that you don't have or that you can transmit the additional traffic without too much delay. So this is what is meant by potential traffic needs idle intervals. Reactive gaps are the opposite of bursts. So the problem here is that we need to characterize their distribution in a meaningful way. And there are as many gaps as packets, so we run into the problem of the information density. So we need aggregation and proper visualization. We have chosen histograms for this problem, and histograms are a proper way to describe a distribution, and in this case, a distribution of packets of gaps. So we have chosen the gap length, calculated in bytes. And we calculate histograms over very short intervals of time. And we're talking about intervals of 1 second or less. And this, of course, provides a lot of information about the traffic profile. But this also poses a problem because you have to handle this much information. And how do we visualize progression of time? This is not easily done by histograms. And the idea here was to display not single static histograms, but dynamic sequences of histograms. So one histogram, a frame for every second of observed traffic. Or for offline presentation, you could also calculate a 3D presentation. So a 3D plot where the depth of the diagram is the progression of time, which I'll show you later. So to give you an idea of what we're talking about, here's a short, not quite live snapshot of the meter working, and it shows the University of Leipzig Internet Access link on 18th of February this year at 2 p.m. And what we see, what we should see, it worked before. So this is actually an animated GIF image of 30 seconds of traffic. So anyway, we see only one frame, the last one actually. So what you can see here is on the left-hand side the utilization of a link. It was a gigabit Ethernet link utilized at 40 megabits per second at this 1 second interval. We have about 14,000 packets per second. And the average length of this packets was 352 bytes. And there's a black curve down here, which is the actual histogram. So the relative amount of length of a certain gap, which is on the x-axis. So we look at gaps of a size of a length between 0 and 15,000 bytes, which is about 10 times MTU. And on the y-axis, we have for the black numbers are the actual histogram, and the blue numbers and the blue curve is CDF, so the cumulated number of gaps per interval. And we have 200 bins for this range of 15,000 bytes, and each bin has a width of 75 bytes. And we see that we start with a relatively high number of very short gaps on the left-hand side. And these are actually the bursts. So we don't look at the packets, we look at the gaps, but we have exactly as many gaps as packets. And we can use this as a means to classify bursts, because it's quite hard to classify bursts, because if you look at two packets, and you think of bursts, you think of packet trains and packets which are transmitted back to back. But packets are never transmitted really back to back. There's always a certain amount of gap between the two packets. For Ethernet, for instance, you have an interframe gap of 12 bytes. And depending on the hardware you use, there is some threshold. So it ranges from 12 to maybe 16 or 20 bytes, depending on the capability of your hardware. And if you have other network technologies, as for instance SONET and packet over SONET, things get even more complicated. But if you look at this picture, you see that you have a rather constant amount of these gaps at a certain size, but you have way more gaps in this first interval. And all of the gaps in this first interval, which are on top of the gaps you would expect, which is the amount which would be approximately down here, these are actually bursts. And these are bursts which were caused by queuing delay in the upstream router. So this is quite interesting, because now you can also predict which of those packets you observe behind a router have been delayed by long router queues, which otherwise would need two taps, one behind and one in the front of the router, to to really be able to calculate packet delays, which we have done too, but not with this measurement. This is a simple single-point measurement. And so it's very interesting that you have a single-point measurement with which you can predict the amount of delay which have been caused to the packet by the upstream router. And then you can see how the blue line goes up to nearly 85%, and then all the longer gaps, all gaps which are longer than 15,000 bytes, fall into the last bin. So what you would expect from traffic which behaves nice would be a very low start. So you have only very few short gaps, which means very few bursts, and a smooth increase, and then as much long gaps as possible, so that you can transmit additional traffic. So, and you have to compare the information density of such a graph with a single number, of a bandwidth observed over this interval. And this interval is 1 second, and usually you have averages over much longer time. So, to give you an idea of how the progression in time looks like, this is a 3D offline visualization. So we have again 30 seconds, and every interval is one of those lines interconnected to each other. And on the front, this front area is again a representation of the bursts we see. And on the right-hand side, we see the utilization for each of those 30 intervals. And we can see that there's quite some variation. So we have a spike here and another one here. So the whole thing behaves quite dynamic. Here's a comparison example. I've looked for I've sieved through different trace files taken at different locations to look for traces which have similar bandwidth usage, but a very different look in terms of this metric. And I found two. So one trace was taken at the University of Erlangen in Germany, and the other one was taken at the National Center of Atmospheric Research in Boulder, Colorado. And they show about the same utilization, with Erlangen actually having a bit more, around 90, 100 megabits per second. But we see that the National Center of Atmospheric Research trace is a lot burstier than the Erlangen trace. This first bin is slightly lower for Erlangen. It's especially here in the later intervals, it's considerably higher, and we can see at the back wall, so to say, of this graph that we have quite some very long gaps for the Erlangen trace, but nearly no long gaps available for additional traffic with the NCAR trace. So here's another example to show you the difference between various utilizations. So this is quite a busy link. This trace is taken at the Catalan part of the Spanish backbone network, and this is actually a 1 gigabit link. And as you can see, the utilization is quite substantial. It's about between 300 and 430 megabits per second. And you can see that you have a rather high proportion of bursts, which ranges up to 60% of all packets, and a very steep slope, and that you have no gaps which are longer than 8,000 bytes, which is quite interesting from the traffic planning perspective. So because the interesting part is the first part of this graph, you have the ability to zoom into this part And on the right-hand side, you see gaps from only 0 to 4,000 bytes per second. And you can discern the behavior at this smaller size much better. So as this is called recent results, I don't have a conclusion slide yet, but a long list of future work items. And there are lots of things which have still to clear up. For instance, how does the curve correspond to the current quality of service? Which boils down, what was the delay of upstream router? I mentioned that we, by observing the number of bursts, we can probably come up with or at least we know that those packets have been delayed by packet queuing inside the router. But maybe we can also come up with an estimation of the delay which happened to those packets. Another question would be, what is the expected jitter of my, for instance, voice over IP traffic? So something very useful for practical purposes. So the next big point would be, how does the curve describe the available bandwidth? So how could you answer questions as how many voice over IP connections still fit in, given the current utilization? So next point, what is the best way to capture long-term trends? And we've already started with some mechanisms. And one idea is to have floor and cap curves of this histogram. And if you break through the floor and the cap, then you can raise an alarm, for instance. And we also had the idea to use this metric for intrusion detection. We have observed that for a single trace, the behavior of this metric is not quite dynamic. So maybe we can use it as a fingerprint or a traffic signature, and that we can use to identify abnormal traffic situations, where, for instance, denial of service attacks or port scans are taking place. So that's all, and thanks for your attention.
Questions? There was a question, please. Sorry, can you speak?
I can understand you. But a network operator can't do it, because a network operator sits somewhere in between. Yeah, so maybe that's a better example, but pardon?
You only care about the end system, the receiver, or Jitter.
You said it as a service, so if you look cheaper, it's okay for the operator. It's only an operator. It's called as a business. It's an operator. You have no cheaper.
What you say is you can actually redistribute packets. What does it do if it's a Jitter?
Yeah, Jitter can actually be part of a service level agreement. It could be. So if it could be measured, then we could have more service level agreements with not only delay but also Jitter.
You can't guarantee anything after you I see Jitter as a bit of a receiver thing.
Okay, here's another question.
Yes, I'm sorry, there are two questions. One is, did you try other intervals from 1 second or whatever, to see if the averaging out of a longer interval might produce different results? And the second question is, what were the constituents of your traffic that you measured? Was it predominantly TCP or was it VDP or a mixture of whatever? In my view, traffic shaping or things like that have a lot to do with this TCP congestion control and all that stuff. So.
Yeah. The second question first. This has been measured at the University of Leipzig Internet Access Link. So this tells you also something about the traffic distribution. We have about 20 to 40% web traffic. We have quite a high amount of peer-to-peer traffic, between 40 to 60%. And yeah, that's about it. So that's the main constituents. And
you don't have any idea if TCP mechanisms or something like that might produce smoothing of those gaps? Or?
No, not really. Yeah, and concerning your first question.
About the second,
Exactly, yeah. I tried it with longer intervals. Shorter intervals doesn't really make sense. I turned it down to, say, 200 milliseconds. So because it has to be observable to the human eye. You do it in real time, so you measure and you calculate the histogram and you display it while you are measuring. So the maximum speed you can capture with the eye would be something about a sequence of 200 milliseconds. And if you use longer and longer intervals, the shape of the curve stays the same, but then you cannot capture events like which you would see otherwise, like port scans or denial of service attacks, where you have a certain jump.
Okay, the last question here.
Yeah, that's an interesting question, because this one shows only up in this particular trace, and we have traces captured 1 year before this one, and we didn't see it before. So they changed the router. So our assumption is we're monitoring at a link between a router and a catalyst, and this is probably some in-band signaling traffic between the two Cisco devices, and those packets get dropped. So they are destined for the router. And usually all packets which go through the router go through it and are not destined for the router. Yeah, it looks like this. So this could be maximum sized packet, which is used for whatever, for network management between the two devices. Yeah.
Okay, thank you. Thanks, Klaus. And I would like to ask the last speaker of this session, Heather Boles from Internet2. She is Director of International Relations of Internet2, and Heather will speak about recent results from the Internet2's Hybrid Optical and Packet Infrastructure Project, or HOPI. Please.
Very good. Now for something completely different.
Find your presentation quickly.
I don't know how many of you were in the Rollout 1 session right before lunch, but in some ways this presentation probably fits better with some of the presentations there that were made about the Géant 2 network, about the CA-Net 4 network, and about the National Lambda Rail project in the U.S., which I'll mention here as I talk about HOPI. So I'm just, thanks for the introduction, Baiba. I'm on the Internet2 staff. And based in Washington, D.C. But this presentation is really made in conjunction with my colleague Rick Summerhill, who is our Associate Director for Backbone Network Infrastructure. Couldn't be here at this conference, but Rick has, as I'll mention in a minute, been co-chairing the HOPI design team. So a lot of these slides are actually from him. So what is HOPI? It's the hybrid optical and packet infrastructure, as you can see. I'll talk a little bit about why we're putting this project together in Internet2. The recent results aspect of this is that over the last several months we had formed a design team of various members of our community and actually also of the international community, and have produced a white paper that we released to the Internet2 membership in April, asking for their feedback, and we're very interested in feedback from other communities as well, since there are a lot of these types of activities going on. Talk a little bit about next steps, and then I'll talk about actually a sort of a parallel effort, but very related effort that we made with Canary and Géant to put up a light path between LA and CERN to try to start to understand what some of the issues here might be. So the project summary, what is this all about? I think you've heard a lot, if you've been to some of the other presentations related to this kind of thing, you've heard a lot of these things said already. that basically there is a fundamental question about how the core of the internet will evolve, how its architecture will evolve. And there is has been a good deal of thinking over the last several years about that evolving in a way that involves both basically dedicated circuits, optically based in some cases, and packet switching services. And what we wanted to do in Internet 2 was put together an effort that would allow our community to explore what that might mean for future architectures of the Internet 2 network infrastructure and so on. So HOPI is both sort of the activity, the exploration of that space, as well as an actual test bed network that we're putting in place to allow the community to explore that. So as I mentioned before, we put together a design team to help us think about how we would do that. It's co-chaired by Linda Winkler from Argonne National Labs, and as I mentioned before, Rick Summerhill. You'll see that there are also participants on the design team from outside the U.S. as well. So some of the architectural issues, and I think if you were at the plenary session this morning and heard Bob Jones talk about the needs for the grid community's desire for being able to schedule in advance a kind of dedicated path across the network, this is just the kind of thing that that the HOPI effort is aimed at, obviously at some of the big user science communities. And again, as I think if you've heard some of the other presentations this week, part of this is coming out of a fundamental question about how the technology will evolve here. When we moved from 2.5 gigabit to 10 gigabit backbone links on Abilene, that was just the other year, it wasn't clear, I don't think it's still clear in some people's minds whether we'll be able to move to 40 gigabits soon enough to satisfy some of the demands, the aggregate demands of these big science users. So people are also looking for more deterministic paths across the network, deterministic in terms of bandwidth, latency, and jitter, and so on. And looking for more end-user control. Again, going back to the grid, what was mentioned in the EG presentation this morning, being able to control the network resources much as the grid community aims to control and schedule compute and storage resources as well. And the other thing driving this for us is the availability of dark fiber at the national level now in the U.S. through the National Lambda Rail project, and also through at the regional level where, much like countries here in Europe as well as in Canada and other places, have been building out their own dark fiber-based networks. So where are we going? What do we have to work with? Sort of in the initial phase, we have a couple of things to work with. The Abilene network, which is the, as I mentioned before, the 10 gigabit backbone network that we have had in place now for a number of years, providing high performance, mostly best efforts IP connectivity for the Internet 2 community. Also now providing, in a number of cases, MPLS tunnels over Abilene. We've been doing that over the last year, and that's part of what we plan to use as part of the HOPI testbed as well. And then a wavelength, a 10 gigabit wavelength on the National Lambda Rail facility. I'll have a picture of that in a minute. There's also a number of other facilities in the U.S. In New York City, there's a facility that Internet 2 put in place in conjunction with NYSERNet, which is the New York State network there, and Indiana University. There's a 10 gigabit link coming across the Atlantic that was donated by Tyco to a group called the IEAF that Internet 2 and SurfNet cooperate. And we intend to use that as well. And then, of course, there's the work that has been going on for a long time in Chicago in terms of the Starlight project there. And obviously working with these regional networks and networks outside the U.S. who, in many ways, in particular in Canada and with the SurfNet 6 project in the Netherlands, have been leading the way in exploring this space. So this is what it looks like when you put the Abilene map together. Abilene is based on Quest Communications 10 gig wavelength and the NLR map together. And I should distinguish which one's which because I don't think that's particularly clear. The Abilene map is the one with the big red nodes on it, and the NLR one is with the blue. I guess you could kind of figure that out from the legend. But and if you saw John Sylvester's presentation earlier today, you'll know that NLR has now got enough members to build out the rest of the southern route as well and connect that all the way around. So this isn't really a long enough presentation to go into much of the detail of the white paper, so I'll refer you to the white paper. But basically, these are a number of the issues and questions that we set out to try to understand and to try to address in the white paper. You know, there are any number of questions here which have been, I think, asked by various people over the last couple of days in some of these sessions, and I expect will be asked in the BOF later today about beyond light paths. But understanding really, you know, what the degree of, you know, how far does this go to the edge of the campus, to the host, to the particular application. That's what is meant by the topological extent of the deterministic provisioning. Looking at how we've architected our Internet 2 network infrastructure in the past in a very hierarchical manner with a backbone with gigapops or regional optical networks, as we're now calling them, connecting to that, and then the campuses connecting to those networks. Understanding how this works across, how these kinds of deterministic paths might be put up across different domains. I'll talk about that. That was the point of our demonstration here in a minute. So if you go through the white paper, and it's available at hopi.internet2.edu, you'll see that the white paper begins to address, doesn't have all the answers for it, but begins to address these key topics. And some of these are, of course, particular to the initial resources that we have in terms of the Abilene network and the National Lambda Rail wavelength. So obviously the discussion of the node location is, you know, particular to our infrastructure, but I think some of the other topics are ones in terms of looking at the different control plane models and some of the software that's out there already, you know, might be applicable to, are obviously applicable to what other people are doing in other contexts as well. You'll also find at the end of the white paper some test cases that the design team has come up with to run as initial tests on this test bed. So let me move then quickly to the light path demonstration. And as I said before, this is sort of a parallel effort. It really stems out of some collaboration that Internet 2 and Canary, which runs CANet 4, and Dante, which runs Géant, have been working on together, collaborating in a number of areas, but of course looking to collaborate in this area as well. And as CANet 4 has already been providing some of these types of light path services, we have been grateful to take advantage of their experience and the UCLP software and so on that they've been developing there and their experiences there. Anyhow, so what we decided to do, we were having a small workshop between our three organizations in March in Ottawa, hosted by Canary, and in advance of that we decided to figure out whether we could actually put up a light path between over the Abilene network, over Canary, over CANet 4, and across a number of other domains as well, the Starlight International Exchange Point in Chicago, and also the SurfNet Netherlight facility in Amsterdam, and then on to Géant and actually ultimately to CERN. There was another meeting in Geneva at CERN that this was talked about as well. So, you know, this isn't, this has obviously been done before. The CANet folks and the SurfNet folks have been doing a number of these kinds of experiments with the light paths, but our focus here was on really figuring out what it took to cross multiple administrative domains and use a variety of actual underlying technologies, since we haven't all on these networks fully deployed capabilities in this area or deployed the same types of capabilities. So this is probably impossible to read, but the slides are there, and this will give you the actual topology of that path. There were a number of issues that we had to figure out with respect to the circuit across the Atlantic and so on, and Rick could probably give you more detail on that, but a couple of interesting issues that we had to work on with Tycho with respect to how that circuit was configured. It took us a while to figure out. And so one of the other interesting things I thought in terms of the way, this is actually from a set of slides that Rick did, presented at our member meeting, was really trying to understand what some of the implications are for this HOPI effort that we've got going and what the control plane was here. And of course this wasn't, the other aspect of HOPI is that not only to provide deterministic in various ways paths, but also to provide them dynamically. So obviously this wasn't able to be done dynamically, it was all manually configured, but kind of looking at, you know, what it actually took to get this done, I think we understand that we have a fairly large challenge ahead of us. And there are some more details about how it was actually put together, and, you know, telling, I guess there is the roughly 8 hours of conference calls and 500 email messages that it actually took to get this thing put together. That's just a quick overview, really, and I would encourage you to go take a look at the HOPI white paper. We'd very much appreciate your feedback on what you see there, and interested in, of course, working with other networks and other communities as you or perhaps exploring the same space. There's also information there on the Abilene network itself and also on National Lambda Rail. So that's it.
Thank you, Heather. Very much entitled. Questions, please? Yes?
So this term, white path, seems to suggest that it was optical-only transmission or something like that, but I understood it was not the case. So
right.
Was it just a PR thing?
Well, I of course didn't come up with the term light path. I think Bill St. Arnaud really coined that term first, and I know that you know, there's been a lot of debate about that. I mean, I think for the purpose of we actually use the term light path in the HOPI white paper, but in a fairly limited definition of that, as you'll find in the white paper. I guess it's kind of become the name that people attach to what we think of as these deterministic paths across the network that hopefully are dynamically configurable. So we're just using that. There was a large raging debate about what the real definition of that was, but we ended up using the term anyhow.
Okay, there's another question.
Yeah, I don't know if that was addressed this morning by Professor or not, but is it safe to assume that we're going to a business model for the internet with this national lambda rail that take us back to the flat ARPANET topology and things of that sort? From what I understand is that in the middle there was this concept of telehousing and separate interconnected carriers and all that stuff. Is it safe not to say that we are building a flat infrastructure owned by universities and so forth, like the same way like the ARPANET was before?
Well, National Lambda Rail is about the members, and in John's presentation he gave a list of all of the members, and Internet 2 is one as well, who have put up the funding for for the initial build out. And it is about the community owning the assets and being able to build out on them. I don't know that, I'm not sure I understand the question about sort of the flat infrastructure. I think that what we believe is, what we're interested in is seeing this kind of facility to develop in a national basis in the U.S. So that it can provide, as John explained this morning, can provide a number of different kinds of capabilities for different kinds of networks, research networks, experimental networks, production networks as well. And the thing that is happening also with respect to the build-out of that facility is that it's also incenting regional networks. So I don't know if the flat part of your question was about the hierarchy or not, but we actually see the build out of regional networks being incented by the opportunity to attach.
With the difference between the telehouse-based model where many carriers meet together and so forth versus what you're doing now?
Yeah, I mean, there are actually different carriers that will be involved in supplying the fiber for National Lambda Rail. So I'm not sure that it's a complete move away from, being able to access different carriers.
Okay, more questions? Okay, thank you. And thank you all for coming to this session. I hope you will enjoy your coffee break. Thank you.
Thank you.